back. I hope everyone's kind of invigorated, had enough coffee. It's my pleasure to introduce Mike Sperber, who's CEO of Active Group. CEO of Active Group, and we'll talk today about fast deep learning with categories.
Well, thank you so much. So I feel Satnam has given me license to talk fast. You'll just have to slow me down. To give you some context, so this is what work we've done. So Active Group, we're a software consultancy in southern Germany. We do mostly project development for all kinds of clients using exclusively functional programming. We also do a fair amount of teaching these days. And we also, if you were there in 2019 in Berlin, we also run an annual developer conference. And it's in March 15 next year. Should you be in town, that would be a great place to be. So this is about a project that we've been doing with Siemens about anomaly detection in industrial production processes. So Siemens supplies all kinds of equipment and software and components for production automation, and those might be like discrete manufacturing processes where you just put a couple of parts together. There might be something like 3D printing. We might also be looking at something industrial security, even though that's not the focus today. So what we want to do is we want to find anomalies in sensor readings in order to head off potential problems. So here's a very simple example. So you might have some kind of beverage production process. So these are all original slides from Siemens. So you might have some kind of cooler unit or chiller unit as part of a beverage production process. You put in energy and you hope that the temperature goes down. And if that relationship somehow goes out of sync, then you know you have an anomaly, and that might be a potential problem. Or on the right, unfortunately, I don't know why they put that in German. I guess because it's about beer production. In beer production, if the temperature and the cooking unit isn't quite right, you might get protein deposits at the bottom of the unit that can be detected. And again, if you get too many of these deposits, then that might also be an anomaly and constitute a problem. So we're trying to find these anomalies in order so that maybe humans can look at them and then see, oh, there's actually a problem in our process. But we don't know ahead of time what the anomaly is. So kind of by definition in this particular project, the anomalies are such that humans can't already describe what they are. So we already saw this one idea where we're just looking at the relationship between different sensor readings. A different idea might be to predict sensor readings. So here, the blue that you see here is kind of a corridor of sensor readings that get predicted by the system. And if, like here, the actual sensor reading is far outside that corridor, that might again be an indication of an anomaly. And of course, we're doing that with, or not, maybe not of course, but I guess these days, we're doing that with deep learning with neural networks. A particular challenge here is sort of the DevOps sides of things. So this is doing something called edge computing, which I guess is not very well defined. So even though Siemens' slide has like a cloud thing up there, it turns out that a lot of Siemens' clients really don't want their sensor readings to leave the premises. And so all the computation has to happen on the premises. And moreover, they have to happen on the computers that actually get deployed in these kinds of processes, which tend to be sort of like on spaceships, very small computationally, but they're very robust. So they're sort of on the order of maybe a Raspberry Pi as far as computing power is concerned. So we want that to be fast. So if you're doing deep learning, well, I guess if you're Satnam, then you do PyTorch. A lot of other people would maybe use Google's infrastructure, TensorFlow, but the same here. So if you heard Satnam's talk, Satnam talked about the need to have a graph in order to do compilation. So even though you're writing, I mean, of course, we want to describe the neural network as a piece of code in our favorite programming language that just computes whatever the function of that neural network is. What happens in practice, though, is that in order to run these neural networks efficiently, well, you need to compile them into this explicit data structure that is kind of a data flow thing that then gets compiled to your target architecture. And Satnam told you all about this morning. There's another reason is in that you need to do kind of a program transformation typically on this graph, because in deep learning, we need to compute gradients. I guess that picture doesn't come out very well, but the details are not very important in that the program that you're writing is not, in training, is not the program that you want to execute. The program that you want to execute computes the gradient rather than your original function, right? And the computation of that gradient is something that you don't have to write explicitly, but rather it's something that TensorFlow or PyTorch will generate for you by doing a transformation on that graph. So while computing the gradient necessary for doing neural networks requires computing a derivative. And I'm going to gloss over a lot of the details because I don't really understand them. But this is, I guess, one of the pleasant architectural properties of this project is that you can make progress on certain aspects of the system without understanding all the details. So, I mean, the derivative that we're mostly thinking about is kind of the Haskell derivative, which is forward, which works in a forward fashion. In deep learning, though, we want the derivative to be to help us in computing the parameters for our neural networks, and these there might be a lot of parameters, and we want that all to happen at once. And for that, we need something called the reverse derivative, which goes roughly in the other direction. Well, if it goes in the other direction, if you look at systems like PyTorch or TensorFlow, they all use pretty complicated algorithms for doing that. Essentially, what you do is you run the computation forward, you keep track of the steps that you did, and then you kind of backtrack from there using something called tapes. So it's imperative and it's kind of terrible, and we don't really want to deal with it, especially not at this conference. So, well, I'll spare you. I mean, Satnam had a couple of Python programs that describe neural networks, and they're kind of they feel very sequential, right? And then you have, have this, put this in that variable, stick that somewhere else. Doing that in Haskell is a lot more pleasant. So this is a very simple neural network. This is the actual production neural network that does the correlation of sensor readings, which is called an autoencoder. You can think of an autoencoder as a simple compression algorithm. So what you do is you just have a neural network that has a bunch of inputs, and it's thinner in the middle than it is at the input side. And so what we do is we kind of compress our data, and then we decompress. And well, if it compresses and decompresses well, that means that it agrees with the assumptions that we put in when we trained the network. And if it doesn't, that might indicate an anomaly. And you can see here, well, you can kind of, the definition here says, well, this is something that's composed out of 4 layers. So this @dot operator is just a fancy composition operator. Details are not important. And the parameters that you need to generate in training also get described by this pretty simple type definition here. And that really is the production code. And so that's something, I mean, not just for Haskellers. So I've actually given versions of this talk at sort of Python-oriented deep learning conferences. And the Python people can also read this. And they look at this and they see, oh, I recognize this neural network. So it's not just a functional nerds kind of thing here. You'll also note that, well, if you looked at Satnam's code in the morning, he had tensor written all over those Haste programs, right? And it doesn't have any tensors here. This is all in terms of general functors. So there's a certain amount of abstraction going on. And in particular, mostly what we're dealing with is what's called representable functors, where you have some kind of notion of an index into the functor. But that's kind of enough to get you started on formulating a lot of those things. Now, I mean, one thing, Conal's here, so he would say, well, the abstracting to functors helps you think about these things. That's certainly true, but on a practical level, it also helps you generate good error messages because, I mean, Satnam told you this doesn't matter. He's wrong. So when you're writing linear algebra programs, people get dimensions mixed up all the time. And if you have something like TensorFlow, these errors only get detected at runtime. But if your matrix is like quadratic, it doesn't even get detected at runtime, right? I think PyTorch now puts something in where you can label the dimensions, and it will look at the labels rather than sort of how many dimensions there are to give you an error message. I'm pretty sure inspired by the error messages that we get from this in Haskell. So about a year ago, I think. So anyway, so we have regular Haskell code that is describing our computation. It's not monadic. I would say that's good because monadics are inherently sequential, so you have to recover the parallelism if you're writing in a monadic style. And this corresponds to what TensorFlow calls eager mode. So TensorFlow actually has like an entire Python front end built in these days that will try to generate the graph from your Python program. So anyway, getting down a little bit into the details of how to compute derivatives. So that's what we want to do. So from high school, we have this notion that the derivative is the slope of the tangent to a particular graph, the function here, and we have this limit construction in order to compute it. That kind of works in high school, but of course here we have the higher dimensional case, and you're dividing by that epsilon. If that epsilon gets higher dimensional, I couldn't explain it to you if for the life of me, right? People talk about partial derivatives and Jacobians. It's all too complicated for me anyway. So I'm trying to explain to you sort of how we went at this from an architectural viewpoint, where we're trying to not have to know too many things in order to make progress. And that's certainly one aspect of it. Conal, do you know where that idea came from? Because I tried to track it down and I couldn't.
The idea of the
derivative
linear maps.
Yeah.
That's Crochet.
Okay.
Crochet derivative.
Okay. So anyway, so here's that idea. I learned about it from Conal. So the idea is this, that instead of just thinking about the derivative as a number, you think of the derivative as the function describing this line here. So you can imagine some D operator takes in a function that goes from A to B, and it will give you a function that goes from A, this point here, to that line here, and this line circle thing is just for a linear function from A to B. So function from A to B goes in, and you get a function that gets you from a point to that linear approximation. And that's a much more useful notion of a derivative. So and you can kind of translate this type into a Haskell type. But of course, the problem usually with Haskell is, well, you've got Haskell code, you can't look inside it in order to do the transformation to compute the derivative the way that TensorFlow operates on the graph, right? So I'm going to try to. So Conal has written lots of papers that have more detail on this, but I'll try to get you the most important details here. So we're used to writing programs using essentially formulas, right? We're using function f of x and equals to something. That's not the only way to construct functions. What we can also do is we can have a bunch of primitive functions and then combine them using combinators. And of course, the fundamental combinator here is sequential function composition, but we can make up all kinds of other composition operators, for example, for parallel composition like the one that you see here. So, well, sequential composition is as you know it. If you have a function from A to C and another one from A to D, you can then you can combine these things. So all of that kind of works out. So if you construct functions this way, you kind of get algebraic terms, right? They can manipulate, just using algebraic techniques, and it's much simpler than dealing with the lambda calculus where you have to deal with substitution. And of course, also, Satnam very nicely said, a little category theory never hurt anybody. That's certainly the case here. We, of course, know the theory that's behind composition, which is category theory. And category theory generalizes this notion of a function to arrows. And maybe the idea is if we can generalize that notion of function to include derivatives, then we can do something in that space. And so here's a very rough translation of that notion of a category into a type class. So if you read the slides that are coming up, so I don't have a paper, so I have to provide some degree of technical detail. So the idea is instead of having the Haskell arrow, which just describes Haskell functions, to abstract over that to describe other things, and we're going to call that K. So the K takes the place of the Haskell arrow. So the identity is not A arrow A, it's A K in backticks A, right? And composition, again, deals with things that have Ks in it instead of arrows. I hope that's clear enough. And you see the distinction here between the Haskell arrows that are here and the Ks that are here. And then you can build on that to write more type classes that describe fancier categories. For example, product categories, would have something like left and right projection. This thing colon asterisk here is just the regular Haskell binary tuple, just a pair. So if you've got a pair of A and B, you can project out the A, you can project out the B, or you can duplicate something to a pair out of those two identical things. And there's something called a monoidal product category, and that can be used to implement this triple ampersand operator that you saw on the slide before. So we can do that, and you will note that, for example, this construction here is written in a point-free style. That's okay. Lots of people like it, like writing in a point-free style. I like having intermediate names for things. I don't know about you, but if you're Haskell programmers, some of them like point. I'm not among them. Also, well, if you get to really fancy categories, then there's something called closed categories, which essentially give you higher order functions. So, we're doing a rough approximation here. So there's a type constructor exp here to distinguish the exponentials that live as objects in the category from the plain Haskell functions. And you get apply, curry, or you need apply and curry and uncurry operators, and that gives you a closed category. Okay. So you build this hierarchy of type classes describing all those categories. And the idea is then to cast somehow differentiation as one of these categories. And in order to do that, we need to explain what composition means for differentiation. And for that, there's the familiar chain rule from high school, I guess. So remember, though, that we're talking about derivatives as linear approximations and not numbers. Okay, that's what you need to know in order to understand this slide. So we have G composed with F at A. That's a function. It's not a number. And well, decomposes to this. So F is a function from A to B. G takes you from B to C. And D of F, remember, is that linear approximation which takes you from A to a linear approximation from A to B. G from B to C, and so on. And then things kind of work out because df at A is a linear function from A to B, so that's this one here. And this thing gives you a linear function from B to C. Thank you. Is that better? Okay, anyway, so it works out. Nice forward thinking, though. So, but if you really wanted this to be compositional, ideally you would have G of G composed with F just to be something involving D of G and D of F. Unfortunately, well, you have this FA thing here, so you need the original function in order to do to apply the chain rule. But there's a very simple trick. Well, you just kind of do a D plus here, which is similar to D, but includes the function value in addition to that linear approximation, right? And then you get a nice compositional formulation of the derivative, and from there, kind of everything falls into place. So you can translate that straightforwardly into Haskell. So you have some general derivative construction here from A to B. And this is exactly the Haskell translation of the formula that you saw on the previous slide. So now what we can do is we can give definitions of all kinds of primitive functions along with their derivative, and we can use composition in order to build larger functions, and they will always compute the derivative alongside the original function. So that's very nice. So there. So the only question is then, how do you write these things? And as I mentioned, you could, of course, write your functions directly using categorical terms in a point-free style. If you want to use intermediate names, which I do, then, well, there's this nice paper by Joachim Lambig from 1980 that tells you, well, if you have a Cartesian closed category, then you can translate a lambda calculus term into a categorical term, right? And that gives rise then to Conal's work on compiling with categories, which I highly recommend that you check out. And the way it works is, well, you take GHC. GHC compiles your program to the type lambda calculus. The ConCat plugin will translate that to a categorical term, which is, again, just a Haskell term. It just doesn't have any, it doesn't have any lambdas in it, right? And GHC then takes that to executable code. And so this transformation to categorical form is a little bit more intricate than what that picture might have led you to believe. So we need to replace, if we want to, remember, we want to write like plain Haskell code, right? We don't, we want to write plain Haskell code and then have that go describe a neural network. So we want to replace the standard operators by the categorical ones. We want to transform the lambda calculus notation to that categorical form. And then, once in categorical form, it will be abstracted over the Haskell arrow, and we want to replace that arrow by whatever our target category is. So replace standard operators by categorical ones. I want to say it's pretty simple. You just use a bunch of GHC rules. It gets more complicated through the fact that GHC does number boxing and unboxing. So I'm just going to gloss over that detail. Then there is Lambig's translation to categorical form. And that's fundamentally the work of the plugin, basically follows the rules that are laid out in that transformation. And then you get, as output, you might get a term like this. So this is actual output code from the plugin. So there's some call, sum AC is one of the operators there. And you can see that its first type parameter is the arrow, right? And that is the K in the type classes. And now the plugin goes and just takes that out and plugs in the target category here. Well, when I say just, it's a slightly more involved process. You might wonder, what is this thing here? It looks pretty complicated. Well, remember that we talked about derivatives, but we were talking about forward derivatives, and for the neural networks, we needed reverse derivatives, right? And the way that the plugin actually does this, well, remember that GD thing, we can turn it from a category into a category constructor, right? So we just abstract over the K, and instead of putting linear function here, we just put a K there. And then, remember, well, roughly the reverse derivative goes in the other direction. We just use the dual category, which reverses the arrows. So instead of sticking linear functions there, we stick the dual of linear functions there, and then things magically work out without any tape. So I think that's super wonderful. So there's a couple of challenges. So generally, when the plugin looks at a Haskell term, it kind of has to figure out where exactly the differences between sort of actual honest-to-goodness Haskell arrows and those that need to be abstracted. That's especially challenging with this differentiation category because it's not closed. So it's not available for the full Haskell subset. So the plugin kind of sometimes gets to a place where it really can't go on. But very often that problem can be resolved by doing a little bit more inlining. So it just inlines a little bit more, goes on in the hope that it will go on. And that's, well, that's a process that sometimes fails, and then it's not always that easy to figure out what went wrong. Also an issue is that the target category might have different prerequisites, type constraint prerequisites than the original ones. So the original program might type check, but the output code needs more constraints that you need to plug in. New type wrappers and coercions are a problem. And really, an issue, though, is that the output code, that's as far as we were thinking when we conceived this project, right? Everything worked out, but then we found out that the output code is slow because it just uses functional code to, you have two vectors get multiplied, another vector gets allocated, multiplications happen, additions happen. It's very inefficient, unboxing and boxing if you're unlucky. But that's as far as we thought. So we're looking at this, and I kind of put off thinking about this for a while until we invited Gabi to give a keynote at Bob. And Gabi doesn't know this yet. I never told her. But while I was watching her keynote, I was thinking, well, Gabi has the solution for exactly that problem. Because she and Trevor and a couple other folks have worked on this Accelerate framework, which gives you access to GPU programming from Haskell, right? And I hadn't been thinking about this. So that's what remains to be done. And as the title says, we're doing this fast. So Accelerate, what Accelerate does is it gives you two data types, ACK and EXP. And these two data, and ACK describes computations on vectors, roughly, on tensors, arrays. And EXP will describe computations on scalars and tuples of scalars and so on. So, well, you can, here's the familiar dot product. You can describe it as using a combination of a fold and a zip width. So that's pretty standard. I'd like to draw your attention, though, to the fact that there's kind of a two-class society going on here, right? In that So for example, the fold takes in a function over exps and gives you remember exp are scalar computation, and gives you a computation over arrays, and zip with is the same way. So, and it kind of makes sense, because if you had acts here, ACK computations here, that would give rise to nested arrays, which is something that GPUs aren't particularly good at, right? Or that you can't really compile to a GPU. So anyway, but for the time being, we were thinking, well, all we need to do is define another category of these functions that compile to accelerate, and then feed that into the ConCat infrastructure, and things are going to work. That's what we ended up doing. So there's a new category called ACFun, and all it does is a function from ACK value to ACK value. And ACK value is a data type that decomposes the structure of the values going in, and it unifies the scalar and the vector values, very roughly, right? And then there's a vector data type set. I'm sorry, it does include the dimension right here, and we found that very useful, so you're wrong. And it unlike a lot of other things sort of with dependent types, these things tend to work out pretty nicely, usually, has been our experience. So anyway, you put that structure in there, and then you can just go and implement all these category-associated type classes. And the way that things work out is, so for example, you know if you have something of tuple type, you know that it, because of the structure of the GADT that you saw, that it has to have come out of that ACK tuple constructor, and so you can just pattern match on that, and things kind of work out. And so the idea is that ConCat transforms your regular arrow to that reverse differentiable functions category. GHC then, and I don't know about you, but it took me a while to wrap my head around this. So GHC then specializes that back into regular Haskell program, right? And that regular Haskell program, then we can feed back into the plugin, and it transforms the arrows that are in that remaining Haskell program to ACFun, and then now we have a working compiler pipeline for this. It wasn't quite so simple though, because I mean, for the longest time, well, so here's the actual category type class definition from ConCat. I gave you a simplified version before, and it has an additional constraint here that says, okay, to constrain the objects that might be in that particular category, or rather the types of the objects that might be in that particular category. And you can see here is the category type class that's responsible for functors, and it has a constraint here that says OK functor. And OK functor says, well, never mind the prime here, so it says, well, if in a particular category, something is an OK value, then and H is a functor, then functor of that A also has to be OK. And this now gives rise again to nested vectors that you might remember I talked about earlier. So because if this is OK, then H of A is also has to be OK, and so on, right? And so Accelerate, unfortunately, has that two-class society of exp and ACK computations, and it just doesn't do nested things, right? And so the first thing to do is to convince the type system that this is true, right? And really it isn't, right? It really isn't true. So what we do is we reflect that the structure of the values into runtime, and we use that reflection into runtime to lie to the compiler here. So you get null code where if you have nested vectors right at the type level, in order to make things work out, we need to pretend that we have nested vectors. Should you use them, the type system will let you do it, but it will crash at runtime into one of these things here, right? I mean, we never intended nested vectors, so things are generally OK, right? Was not pleasant writing this code, I should say. So having solved that, though, here's another issue that we thought about for the longest time. This is not even about nested vectors. You can see here the derivative of the fmap function, and it's fmap unzip something called crossf. And if you look at crossf, it says functor of AKB, so essentially a vector that has function inside. I'm simplifying a little bit, right? So this is not even nested vectors. This is kind of higher order vectors or something like that. And needless to say, GPUs don't really do that either, right? And Accelerate doesn't let you do it either, right? On the other hand, so for the longest time, we tried writing a version of FMAP that just wouldn't involve intermediate values that were higher order vectors. But it's really difficult to do that without duplication, without duplicating computation, surprisingly. And so I think I sent, over the course of this project, I sent a couple of desperate emails to Conal, and Conal said, you have to restore compositionality. And so that turned out to be the right thing to do. So this is really frustrating because, of course, this higher order vector is only an intermediate value. It gets constructed in the middle, and it gets deconstructed in the middle as well. So the computational processes really don't require this, right? You could just kind of, if you kind of did the composition of the construction and the deconstruction inside the functors, then things would be okay. And so we ended up just putting the necessary information into the ACK-value data type. So whenever we don't know how to do a map, because there would be an intermediate value of higher order type, we just we put off doing anything, and we call this constructor here. And we kind of propagate this through the construction of the Accelerate program at the end. Whenever we see situations where the map hits something that that we can compose, we would just do that. So I mean, here's kind of an obvious case. If you have a map of something that is already a map, we can just compose the underlying functions and eliminate one of the maps. And there's just a bunch more cases like this. So if you have this, we just ran this program and looked at all the cases that it went into and fixed, and these turned out, all of them composed into something nice. So as they should, right? Because we're not doing anything bad really. All of these things, all these intermediate evil constructions of higher order vectors, we also decompose. So so it's slightly complicated code, but it's all in the infrastructure, right? So here's, if a zip meets a map, then there's something else that you can do, and there's a couple more cases like that. So what have we? So got lost in a lot of technical detail here, but what have we done? Well, we're writing neural networks in really, really nice direct style, non-monadic ZatNam, Haskell. And we have ConCat transform it into reverse automatic differentiation. We have GHC inline the result into regular Haskell. And then we ConCat transform again into that ACFun category. And then we run it and accelerate on the CPU and GPU. And that gives really nice, nicely performant code at the end. Here's another this might be interesting for ZatNam, I don't know, or maybe not. So Siemens tasked us, they bought a bunch of TPUs. I think they suck, probably. They do? No? Which family? Yeah, I don't know. So anyway, so I'm sure they're not as good as Grox's. I was just trying to play into your hands here. So so Siemens tasked us because, remember, these little boxes are not very computationally strong. So there's these little USB sticks that you can get from Google. That take about a year to ship, but they're pretty cheap. And they said, well, we want to use those for our neural networks. And so we had a nice cooperation going. We've had a nice cooperation going on with Gabi's group to then have Accelerate target those TPUs. Ironically, the way that Google's API for this is something called TensorFlow Lite. And the way that you provide models for TensorFlow Lite is you use regular TensorFlow, so there's now a TensorFlow backend for Accelerate. And remember that this whole effort started with the premise of getting rid of TensorFlow. So in this particular microservice, TensorFlow is back, but only in this one. So we've had lots of help along the way. So Conal helped us lots and lots. Richard Eisenberg and Tweak helped us figure out a couple of GHC internals. Joachim helped us figure out the new type stuff. And Gabi and Trevor and their group helped us do that Accelerate stuff. So now we have a fast deep learning infrastructure from available parts, from available reusable parts, right? And this is very pleasant from an architectural perspective. Okay, coming back? Okay, I think it came back. Okay, great. So we have deep learning infrastructure from, well, I really should have said reusable parts, right? A lot of these parts can be used for different purposes, right? The category, so the compiling to categories infrastructure can be used for lots of things. Of course, Accelerate can be used for lots of other things. And so this whole thing kind of decomposes into completely independent parts. And so that's, I do a lot of software architecture in large projects, so this is really nice. The Haskell neural networks are really pleasantly readable, which really, really fundamentally is not the case for a lot of these Python-based neural networks. And there's way less mechanics overall than the TensorFlow tape approach, right? Even counting, the intricacies of the ConCat plugin and stuff like that. There's a couple of caveats. So new GHC releases break the plugin every single time. So just patched it up to 9.4 though. And it probably should, given the way, given how deep it has its fingers in GHC internal. The plugin is not very robust, I mentioned that, but there's another kind of customer of the compiling with categories framework, Kitty Hawk, a company that makes like electric flying taxis, I think, programmed using this infrastructure, and they rewrote the plugin to something that's much more robust. It just doesn't quite have the same requirements as ours, which is why we haven't been using it. As far as the plugin itself is concerned, though, it worries me a little bit that essentially all the work on the plugin with an active group that has happened, I've had to do it. And I've not been, even though I work with greatly talented and well-educated folks, just this intersection of sort of GHC, a little bit of GHC. I don't really do a lot of Haskell otherwise, but of GHC and Haskell, a little bit of categories and compilers, and there somehow that intersection seems to not be very heavily populated. And it's difficult to populate it also. So that's a little worrying that every time there's a problem with a plugin, Gabi said, well, I'm CEO. It's not really I have lots of other stuff to do. So that means other people have to wait. That's never a good thing in software project development. And you can probably tell that we didn't really think a lot about what we were doing, but it kind of worked out in a lot of pleasant ways. So we're pretty happy with the way things have been going, and we've learned a lot in the process, which is also useful. That's it.
Great. Thank you, Mike, so much. Do we have some questions for Mike? Sure, and let me pass the mic.
Super cool. I learned a lot from the talk. Thank you. How do I try it?
So the ConCat plugin itself is on GitHub. Try it out.
Is there? I couldn't find a link easily. Is there? Maybe I'll talk to you later.
Yeah, talk to me later.
Okay.
Should not be that hard to find.
Okay. And what about? Okay, I will. Yeah. And performance. Did you have any measurements? Comparison with?
It runs fast. Yeah. So this is not academic research, so I don't have benchmarks really. But so I can tell you the speed up. We've seen speed ups from going to the original functional version to the Accelerate version on CPUs. So not even involving GPUs of at least about a factor of 10. Sometimes more. It's a little bit. Haskell is kind of tricky to benchmark. Haven't had time to do that.
We have some more questions for Mike up here.
So the neural networks that you described, are they all necessarily acyclical?
I don't know.
Okay.
So I can tell you, one is the autoencoder that you saw, right? The other one is something called a causal convolutional network. Mm-hmm. And I told you about one of the pleasant architectural aspects of this is I have no idea what that is.
Okay.
So I don't think it's recurrent. So my guess is it's probably not cyclical.
All right.
Yeah.
So I think your previous slide summary of how this has advantages over Python-based frameworks, and you have a deploy system, and you don't maybe care about comparing that that very detailed, but I'm just wondering, like, for example, you talk about performance or readability. Did you compare with something that would be done in Python? Like, for example, not just comparing performance against the sort of pure Haskell functional code, but also what would happen if you just, express the same neural net in Python?
So as I said, we haven't done detailed benchmarks. I can tell you it's in the same ballpark as the original TensorFlow, so there's not like super magnitude of difference, but we haven't done any detailed measurements there. As far as readability is concerned, so at least the fancier neural network is something we also have a Python version of that, which is less readable. Might be us, of course, though, but yeah.
I have a question for you. You said sometimes it breaks and you have to fix it.
Mm-hmm.
Do you actually have like a small team of people that are essentially developing and maintaining this compiler infrastructure in-house? And I'm curious, like how big?
Yeah,
of
that team is me.
It's just
So,
you.
yeah,
Yeah,
just
okay, good. Curious how big of an effort that was, but it's one person.
It's one person, yeah.
That's fantastic. Any more questions for Mike? Great. Okay, well, let's thank Mike again for his talk.